Yes, we are.
Hi, Paula.
Hi, Neil.
Hi, Michael. And welcome, everybody, to San Francisco. I'd like to say sunny San Francisco, but you'll be pleased to hear it's pouring with rain outside. We are here in the Exploratorium, and you people can't see this, but in fact, all around us here, there are thousands of kids. We're right in the middle of this amazing science center. There are kids taking part in experiments and demonstrations all around us. Today we have a wonderful show for you. That we have Paul Doherty, who is the resident physicist here at the Exploratorium. And coming live, Paul is going to be giving us demonstrations of two of Einstein's major discoveries exactly 100 years ago. This is the Brownian motion and the photoelectric effect. What I find amazing is that Paul is going to do these demonstrations using stuff from the kitchen. 100 years ago, these were major scientific breakthroughs. Now we can do it with kitchen implements. So it makes me wonder what, in 100 years' time, people make of the experiments we're going to talk about, the experiments we're doing now. Then we have a description of our big antimatter experiment at SLAC. SLAC, the Stanford Linear Accelerator Center, and I am now the Director of Communications at SLAC. And we will be describing the tremendous work we've been able to do on antimatter research. We'll follow on with two outstanding young personalities, Stefan Alexander, who is the hip-hop physicist. He's a theorist and also extremely talented saxophonist. And then we'll be bringing up Keelan O'Connell. Keelan is a bit of a celebrity. She has a blog on Quantum Diaries, which has sometimes over 1,000 individual visits each day. So we're going to spend a very entertaining hour here from San Francisco, from the Phyllis Wattis Exploratorium webcast studio. So I think we'll get started by asking Paul, if you'd like to come up and give us some demonstrations of how Einstein did his stuff. Hi, Paul.
Thank you, Neil. Well, 100 years ago this year, Albert Einstein made some tremendous discoveries in physics. And I'd like to show those to you. Now, the first thing, in the 1800s, the scientist named Brown looked at tiny particles in water and observed under the microscope that they continually moved. So at the Exploratorium, at our imaging station, we have some modern, wonderful, expensive microscopes with television cameras. And I took the following image of Brownian motion. Essentially, you can take milk from home and dilute it into water, and then put it under a microscope and observe Brownian motion. Now, you'll notice, as you look at this video, it's rather subtle. You're seeing twinkling blobs of fat in the milk, tiny blobs of fat that are ever so gently jiggling around. And yet this seemingly nothing picture led Einstein to do the mathematics that showed that atoms existed. Before 1905, most scientists thought the atomic theory was a wonderful way to explain chemistry, but that atoms weren't real. After 1905, after Jean Perrin, had done experiments on Brownian motion, scientists accepted the reality of atoms. And so it's an amazing breakthrough. So how do we go beyond this actual picture? How can I make it real for you? Well, at the Exploratorium, we have an exhibit that was built by Ron Hipschman early on, and he's my cameraman today. So Ron, come on over and we'll show them our model of Brownian motion. You see, you're looking at the fat globs in the milk that are just gently dancing. Here we have a white cylinder of plastic representing the fat globs and these ball bearings, a little in the dark there, but ball bearings which are moving around. Now, in the milk, there are water molecules moving around, and they actually hit those milk globs 10 to the 14th times every second. That's 1 with 14 zeros times per second the fat globs are hit by an atom or a molecule. And in here it's happening somewhat slower. And yet we can follow that dance of that piece of plastic. It dances around. And until Einstein, the scientists looked at the dance of these fat globs and tried to measure their velocity. And the problem was, the shorter the time they measured the velocity over, the faster it went. And it looked like the velocity was going to go to infinity as times went to zero. And that's ridiculous. Einstein realized instead of measuring the velocity, we should measure the mean square distance. And that led to a final mathematical analysis. So here you can see that ball, the ball's hitting that piece of plastic, and it does its Brownian motion dance, random walk. Well, I've discovered a way that using a $2 pointer laser, you can observe random walk at home. You don't need a $100 microscope. All you need is a container of dilute milk that's thin enough that you could read the newspaper through it. So I've got the little container of milk here. And there it is. So you can see it's milky, but just gently milky. And in a minute, I'm going to put a laser through there. But before I put the laser through there, I've got to show you something about lasers. It's called diffraction. And diffraction is an amazing tool. It turns out that when I put a laser beam through a tiny pattern, a small space pattern, it makes a huge space pattern. Diffraction takes small things and makes them large, and it takes large things and makes them small. And since we're searching for small things, a laser is the way to go. So I thought, what around my house has this tiny pattern to it that I could show you this relationship? Now, you can do it with a $2 red laser pointer, but for visibility here, I'm using a green laser pointer that costs a little bit more than $2. So here's the laser dot, which Ron will show you. There's a laser dot right there. I believe you can see that, Ron. And I went around the house and I found something with a very fine pattern. It's my wife's stockings. But if you look at a stocking material, it's actually very fine weave. It's just this tiny, tiny weave. And if I put that in the laser beam, it will diffract it and make this little spot on the screen. Now Ron will adjust the intensity there, and you'll be able to see the spot. There it is. It's a little bit, there it is without the stocking, and there it is with the stocking. It gets a little bit bigger. There it is a little bit. It's twinkling a bit because I'm moving the stocking. Well, then I thought, well, what can I make that's smaller around my house? What's smaller than that? And I went to my computer and I got a compact disc. And you can actually peel the aluminizing off a compact disc and make it transparent, and it has a pattern on it. And this pattern is 100 times smaller than a human hair. It's about 1.6 micrometers across. And when I put the laser through that piece of compact disc, it spreads two spots out. And those two spots spread much further than the stocking spread. And in fact, then I realized, there's something even finer still around my house, and that's a DVD. And this is half the size. The spots on a DVD are half the size. And so you see the spread of the dots on the screen is much wider. So the laser lets me take tiny things and make them large. And that's what I need to do to show you Brownian motion. So here's what I'm going to do. I'm going to take this laser, and I'm going to shine it through this container of milk onto this screen. And I'll turn it so people can see it. If you look into this screen right here, and I'm showing it to half the audience, and then I'll show it to the other half, you might notice that the light is twinkling. If you look in there, you'll see the light is twinkling. And here Ron, if you look on the screen, he's got the camera looking at it, and you can see it's twinkling. And that twinkling has a certain time pattern to it. And Einstein's equations exactly predict the time of those twinkles based on the angle of view. Because to change the pattern of milk, to make a dot of light that's close to the beam, the particles have to move a huge distance. And it takes a long time to do that. And to change the pattern at large angles, it takes a tiny motion. So angle tells me how far the particles are moving, and the twinkling time tells me how long they take to do it. And from this twinkling, what you're seeing in this twinkling light is the actual motion of the milk globs in the dilute milk solution. And that twinkling allowed scientists to calculate the size of the atom. And you can do it today with a $2 pointer laser, a container of milk, and a little piece of saran wrap, or I guess this is wax paper. So that's a really nice experiment. And that, today, as we go into nanotechnology, Einstein's mathematics of Brownian motion is still in play. In fact, this is his most cited paper, even more cited than relativity. So Brownian motion, very important even to this day, and you can do it at home. There's Ron looking into the container. Whoops. And later, we'll have a chance you can ask questions. Okay? So now, we'll go to the next experiment. And this one leads into some modern experiments with particle physics. What I have here, it's the photoelectric effect. And I'm going to show you the photoelectric effect. In fact, I'm going to turn off this laser. I don't like shining green lasers out into the audience. Move that to the side. What I have here is a piece of galvanized steel. Now, galvanized steel is steel coated with zinc. So this is zinc, and I've taken a piece of sandpaper and I cleaned it off. So I've got pure, raw zinc on top of this. And in honor of the season, it's almost the Christmas season, I have tinsel, which is mylar, plastic, covered with aluminum foil, and it's hanging down like the tentacles of a sea animal hanging down. And I'm going to lower that into this container. I have to put it in the container because it's blown around by the winds. So this container purely isolates it from the wind. And you can also do this if you can't find the galvanized steel. If you get a heavy-duty battery, not an alkaline battery, but a heavy-duty battery, and you take a hacksaw and cut off the end, the blunt end, you can get all the stuff out of the battery, leaving a hollow cylinder. And that hollow cylinder is made of zinc. It's pure zinc. Open it up with a pair of scissors, and you can make your own version of this experiment with the tinsel and the flattened bit of battery material. It's amazing. You can get pure zinc material just by taking apart a 50-cent battery you find around the home. Don't open an alkaline battery. The materials in a carbon zinc battery are quite safe and non-toxic. I chose to use the bigger galvanized steel for today. Well, now I have to step back to 1770. And a great American scientist whose birthday we're going to celebrate next year, his 300th birthday, Benjamin Franklin. And Benjamin Franklin was the first one to discover a model for static electricity. And what I've done is I went out and I got some blue styrofoam house insulation. And I got an alpaca sock, but any wool sock will do, including your head. And if you rub the blue styrofoam with the wool, charge is transferred from one to the other. And by Benjamin Franklin's definitions, we know that the charge on the styrofoam is negative. It's a negative charge by his definition. He arbitrarily made it negative. I can tell it's charged if I move my hairy arm over the styrofoam. I can feel the hairs moving. They just move under there. And there's the most amazing name in the world in English for the sensation you feel when there's an electric charge near you. It's called formication with an M. It's very important to pronounce that clearly. And the formic comes from formic acid, the feeling of ants crawling over your skin. So I know that this is heavily charged because I was really experiencing strong formication. Now, if I take an aluminum pie pan and drop it on the negatively charged styrofoam, the styrofoam is trying to drive the negatives out of that pan, but they have nowhere to go. They're surrounded by air. I can give them a place to go. When I touch this, I've now let the negatives go away from the aluminum pie pan, and I have a styrofoam cup handle. So now this pie pan is positively charged. Say that fast 3 times. The pie pan is positively charged. Yeah, okay. And as I bring the positively charged pie pan down towards these tinsel pieces, you see that the positive pi pan is driving the positives down into those hairs. And if I bring my hand in and touch it, they come back together. And now I've charged them negatively. You see, the positives on the pi pan drove the positives on the zinc into my finger, leaving behind the negatives. And you can see they're spread out. There they are, spread out. So I'm going to take this ultraviolet light. Now, this is a short-wave ultraviolet light that mineralogists use to analyze minerals. And when I shine that ultraviolet light on the zinc, those aluminized mylar hairs come right back together. Let me show you that again. So I rub this and make it negative. Styrofoam rubbed with wool is negative. I put the pi pan on it, and I touch it. Ouch, I felt that. This is now positive. When I bring the positive over here, the hairs go apart. I touch it, the positives leave the pan. I remove my finger. I remove this. Oops, we'll try it again. Bring it over, touch it, remove this. There they are, nicely charged. They don't come together. If in the room lights, all this room light we're pouring on there, they still stay apart. They don't come together. But as soon as I shine ultraviolet light on it, they come together very quickly. Now, nobody understood why that was back in 1905. I'll show you one variation on this experiment, and that is I can actually take the negative charges here, rub this, make sure it's heavily negatively charged. Nice firm rubbing. There we go. I can bring the negative charge over, touch it, go away, and now I leave it positively charged. So those fibers are now positively charged. I can shine my ultraviolet light on this, and they stay spread out. They don't come together at all. That's interesting. Positive charges, ultraviolet light, any light shown on it, the charges don't leave. Negative charges, however, when I shine the ultraviolet light and only the ultraviolet light on it, the negative charges leave. That puzzled everybody in physics. No one could understand that. And then this patent clerk, Albert Einstein, extended some of the ideas that were going around in science at the time. And he proposed, if light were made of quanta of energy, if light were quantized, you see, up to then, light was a wave. Maxwell had this great theory of light, waves of electricity and magnetism. But Einstein said, what if it came in packages of energy, quanta, and the quanta interacted with the charged particles in this metal, all or nothing at all? An amazing idea. Then get this. Red light, according to Einstein, came in small energy quanta. By the way, Gilbert Lewis in 1926 named those quanta of energy photons. So the word photons describe Einstein's quanta. So the red light comes in with small energy quanta, hits the electrons, the extra electrons that give this its negative charge, does not have enough energy to drive them out of the metal. The ultraviolet photons, on the other hand, have a lot of energy. They come in with enough energy that when they hit the negative electrons in the zinc, they can knock it out of the metal. And that's why this experiment has to be done with zinc. It's one of the metals that ultraviolet light can knock the electrons out of. So every ultraviolet photon comes in. It can then knock out an electron. This has a bunch of electrons on it to start with. The electrons leak away under the bath of ultraviolet, and my charged particles come together. My tinsel comes together. When I put positive charges on there, I do that by removing electrons from the metal. I shine my ultraviolet light on there. It's not adding electrons to it. There's no way that the ultraviolet light can bring electrons to it. It can't eject the excess positives. Those are ions. They're heavy atoms. They're ions. I can't knock the zinc out of there, so nothing happens. So what an amazing idea. But this is an early particle physics experiment. I'm taking the particles of photons and colliding them with the particles of electrons in the zinc and knocking them out. And soon we're going to jump 100 years into the future and how far we've come in 100 years to do particle physics experiments with matter and antimatter and B particles and all sorts of new things. But it all starts back here at the turn of the last century with these simple experiments. By the way, if you want to do this one yourself, there's a really wonderful and inexpensive source of ultraviolet light. It's called the sun. And sunlight has plenty of ultraviolet to discharge this experiment. The problem is, of course, if you want to do the experiment, you have to find a way to keep out the sunlight. So what I would suggest you do is, like in a house with a nice sunbeam coming through an open window, window glass will block the short wavelength UV we need to do this experiment. But have a nice open window with a sunbeam, do the experiment in the dark, slide it over into the sunbeam, and you'll watch the sun, the ultraviolet from the sun, drive the electrons out of your metal. So that's my simple experiments to show you. And then, in fact, those are still apart, and I touch it and they come together. Those are my simple experiments to show you how you can do with modern household materials under $10 each the experiments that inspired two of the great ideas that Einstein had in 1905. The third one, relativity, I'm still working on the $10 model. So,
great.
Neil.
Paul, thank you very much indeed. That was great. Finally, I think I've got a hang of what Brownian motion and the photoelectric effect are. But more important, I've now understood what that word everybody uses, formicate, actually means. That's been very useful for me. Thanks a lot, Paul. So now I have an opportunity to explain to you all a little bit about SLAC, the Stanford Linear Accelerator Center, which is one of the world's great fundamental science research organization, which is about 30 miles south of here, just outside Palo Alto. SLAC, the Stanford Linear Accelerator Center, was set up in 1962. And what kind of typifies this remarkable place is our linear accelerator. This is a 2-mile-long linear electron accelerator. 2 miles long, it is the longest building in the world. It is exactly 6 yards longer than the Hong Kong airport terminal. Well, the last time it was measured, it was. The SLAC has had a tremendous effect on our understanding of how matter behaves, what are the constituents of matter, what are the forces that hold matter together. And some of the biggest breakthroughs in our understanding of visible matter came at SLAC thanks to experiments driven by the linear accelerator. 5 scientists won Nobel Prizes for experiments which they carried out at SLAC. And there's an area at SLAC which I think we could make a pretty good claim to be the most Nobel-dense area in the visible universe, because all these experiments happened in a very restricted area. The LINAC, the linear accelerator, we still use. Even though it's been running since 1966, it's still at the very forefront of experimental physics at SLAC. It is the injector that we use for what we call the B factory, which is a storage ring, a circular accelerator, which is fed by our linear accelerator. And on this circular accelerator, we have the experiment Babar. And Babar is the experiment that we are using to try and understand what are the differences between matter and antimatter, and basically where has all the antimatter gone? Where is it? And this is what we're trying to find out. We're looking very hard for this stuff. However, other things that happened at SLAC was we realized very early on that in actual fact circular accelerators, when the electrons go around the corners, they emit a certain kind of energy, and this energy actually comes out in the form of X-rays, and that we can use these X-rays to see inside materials, to see inside biological processes, material structures at tiny, tiny, tiny dimensions. And this research is called synchrotron radiation research. And again, SLAC was the first lab in the world which did experiments on this kind of research. And it has grown and grown at SLAC until we are delighted that the first ever free electron laser, a machine called the LINAC coherent light source, will be built at SLAC. We've started construction just these last few weeks, and by 2009, we will have this machine up and running, which will actually be a movie camera which will be able to film in real time biological processes and chemical reactions. The first time this will ever happened in the history of science, and I think it will blow away a lot of our ideas on chemistry and biology. Also at SLAC, we have opened a new center. It's called the KIPAC, which is the Kavli Institute for Particle Astrophysics and Cosmology. As you've probably heard, if you've been listening to this webcast throughout the day, there is a really big mystery out there, which is that all the visible matter that we can see only represents about 5% of the total mass of the universe. 95% of what is out there, we haven't a clue what it is. And this is surely the biggest mystery of our age. KIPAC at SLAC is a center which will bring together some of the greatest minds in the world to look at these big astronomical questions of dark matter, dark energy. So SLAC has got to be one of the most exciting places in the world to do science at the moment. That we put together a cocktail of particle physics with the B factory, trying to understand what's happened to the antimatter. We have the world's most advanced machine for looking into tiny dimensions at high speeds with the LINAC coherent light source. And with the Kavli Institute, we are able to do the most advanced research on what's going on out there in the universe. A wonderful place to be. And indeed, the Exploratorium crew came down to SLAC just very recently and were able to film inside the Babar experiment. Now, Babar is named, as you may have guessed, after a very famous elephant. Babar the elephant, who is a French cartoon. But it has some kind of logic, because in physics terminology, what we're looking at is B mesons and anti-B mesons. A B meson, we say, is a B, and we say an anti-B is B bar. We put a bar across the top of it. Therefore, B bar, B bar, B bar, 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 bar. This is how it got its name. And in Babar, we collide electrons and positrons together to form B mesons. Some of them are positive B mesons. The other ones are the antimatter form, anti-B mesons. And we measure with incredible precision and accuracy the differences between the behavior of these two particles, the matter and antimatter. And in this way, we've been able to make very important measurements of the behavior of the difference in the behavior between matter and antimatter. So, on this tour of SLAC, our friends at Exploratorium were able to make a movie which we'd like to run for you now. So first we start off from the middle, and it's my friend and colleague Bill Wisniewski, who is the technical coordinator for the Babar experiment, who is going to explain what's happening.
This part of the tunnel is the only place in the 2.2 kilometers of the ring where the beams are brought together into the same plane. And this is so that the two beams can be brought together in the center of the detector for the interactions to take place. The beams collide there. Low energy beam line and the high energy beam line. here are the two beam lines coming together. The high energy beam, the electrons, are being brought into focus at the interaction point with the low energy beam, the positrons. The collision takes place in the middle of the detector, deep inside the tunnel there, and it's the middle of a 1,200-ton chunk of instrumented iron. That tunnel leads to our device that measures the path of charged particles inside the magnetic field. It's basically a can of gas with about 7,000 wires strung the length of it, and that's used to track the particles. We're now at the front end of the detector. It looks very, very different from the back end. The electrons from the high energy ring collide with the positrons from the low energy ring, and then their products move forward along the line of the electrons. This is an Einstein relativity situation where the events are effectively folded forward towards the front end of the detector. What you see here is the final section of the beam pipe from the accelerators. At this point, both rings have already been brought into a single beam pipe. And in the background, the large gray shape and red shape is one of the two doors in the forward direction for the detector. So this completes the magnetic circuit. It's steel with many, many layers of detector inside it. And you can see that one door is open completely on the left side, and on the right side, it's cracked a few inches open. When it's running, they're both closed, and those doors are held tight to the barrel by the magnetic field.
Good. So you've been able to have a very privileged look, in fact, inside the tunnel of our beef factory and the Babar detector. It's not very often that this thing is open for filming because we use it as much as we possibly can. There is this frantic desire to get the data, to get the results out of this experiment. It is a very, very beautiful piece of equipment. And what I find truly remarkable about Babar, and indeed other physics experiments around the world at CERN and our colleagues at Bell in KEK in Japan, is that these are all big international collaborations. That at Babar we have 10 different countries, different nationalities, all working to build and now to run this thing. And so you can walk into a control room in California and find it full of French, German, Chinese, Americans, many, many different nationalities. It is a fantastic model and very inspiring place to work. So, now to continue with our analysis of what's going on in the world of antimatter and the work which we're doing at SLAC, I'd like to introduce to you the one and only Stefan Alexander, the hip-hop physicist, the hip-hop theorist who is here to explain more to us. Stefan, you get up here.
I guess I should break dance or something, huh?
Yeah.
Let's put this sound here.
You're not going to dance?
Oh.
Well.
I'll just put this here for now.
Good. So, Stefan.
Yes.
Stefan, I have to say also, apart from being a hip-hop specialist, is also one of the most talented jazz saxophonists around this area, and maybe later on you're going to play us a couple of tunes.
Sure, my
We'll see
pleasure.
how it goes. So, Stefan, I've explained a little bit about what is happening at the Babar experiment, but why are we doing these experiments? Who cares? Why does it matter what's going on here?
Well, I think anyone that exists should care because, I mean, we're made of matter, and we also know that there should be, according to the best theory we have, the best understanding we have of matter, the standard model of particle interactions, we know that there should be as much antimatter in the universe. And we know that if you put matter and antimatter together, then you're basically left with nothing. And so the question is, when's the antimatter? Where's all the antimatter? Because when we look at galaxies, and if you look beyond galaxies, you actually know from experiments by looking at the spectra of galaxies, the spectrum of the light emitted from galaxies, that galaxies are, made of matter.
So there is no antimatter. We haven't found any stuff anywhere.
We have found a little bit of antimatter, but tiny, nothing compared to the amount of matter that we see around us. So, question is, so Babar, one of the things that Babar does is studies the weak interactions, mainly the weak interactions, one of the four forces of nature, and by looking at how the B particle transmutes or changes into the anti-B particle, we can actually measure the amount of in that process, there's a particular symmetry of nature that's violated, and we give it a fancy word. It's called CP violation. And we can actually measure very precisely the amount of CP violation. And what we find is that it's not enough to account for the amount of matter that we know is around us and we observe.
So if I understand what you're saying, that the experiment we've done at Babar has shown there is this difference in matter and antimatter, but the difference isn't strong enough, isn't big enough to explain the amount of matter.
Not even a cinch.
How much? What is the cinch? So we got like 10% of the matter, or
no?
Not even.
Like decimal points.
Oh wow.
Yeah, it's not enough.
Okay, so we're left in that case with a bit of a problem.
Yes. In fact, very quickly. I mean, we know exactly how much we need by just looking at the amount. So galaxies are made up mostly of light gases, and there's a certain fraction, a percentage of helium to hydrogen to deuterium to lithium. And by measuring those things and doing experiments here on Earth from the reaction rate of these light elements into one another, we can actually measure exactly the difference between the matter and matter. And by knowing that and comparing that to the Babar experiment, we can actually know exactly how much we need against what we actually see in our theories.
If I've got it, this means we are not anywhere yet clear to understanding what happened to the antimatter.
That's correct.
Or why the entire universe as we know it is made of matter.
That's right. We give this a fancy word in physics. It's one of the major problems currently facing us, and the word is called baryogenesis, the genesis of baryonic matter. So nuclear matter, we call it baryons. I would say that someone who's Barry,
he did it.
Yeah.
Okay. Well, so what are we going to do? Here we are, stuck. The experiments have shown us that we are not able to explain what all this matter, where it came from, what antimatter. But I think you're working on a different way of looking at this.
That's right. So SLAC is mainly built up of matter, antimatter. The matter at SLAC is experimentals. We have lots of experimentals at SLAC, but we also have a theory group here, and I'm one of those. I'm one of the theorists. And at SLAC, we are extending the theories of the standard model to make predictions. And one of the things we're doing is trying to understand cosmologically. Since we observe matter cosmologically on very large distance scales, we're trying to understand when you go back to the early universe, when the universe was smaller and denser, and there wasn't matter around, and there wasn't antimatter around, how it is that matter, we can generate this baryogenesis. So that's one of the things that over the last 3 years, I and a colleague at SLAC we've developed a theory where Einstein's theory of general relativity comes to the rescue. So we're showing in this theory that the electroweak, yes, we know it's not enough, but actually Einstein's theory of gravity in operation in the early universe can actually help the story.
So by looking again at what was going on at the very early times of the universe, looking at it in a different way, maybe you can have a model for an explanation of why we see only matter and antimatter.
That's correct.
So what is this? What is it about Einstein's idea that's going to...
Okay, so there are two ways to think about it that we're going to combine, because Einstein's theory of general relativity is a mathematically very intense theory. Not today, the biggest computers can't even deal with it. However, it's a simple theory, because Einstein's theory radically tells us that space and time is not really how we experience it. It tells us that space can be bent and curved around in the presence of very heavy objects. But Einstein's theory tells us something that's even more interesting in my book, which is at the forefront of physics today, which is that if you shake matter around, the fabric of space and time will jiggle, meaning space will actually undergo a vibration itself and get warped in a wave-like pattern. We call these things gravitational waves.
This is something that Einstein predicted way back, huh?
That's right. His theory predicts this. That's right. It's a prediction of the theory.
Have these gravitational waves been seen?
They have not been directly seen. They've been indirectly measured from two stars rotating around each other.
Let's say they're out there. Let's
yes.
give Einstein the benefit of the doubt.
So Einstein's theory predicts these propagating waves that move at the speed of light. And in the early universe, when there was just space around and the space was expanding, the theory predicts that gravitational waves are going to be produced there. Now, what's interesting, what I want us to think about now, we know that electromagnetism itself, if you move a charged particle about, it will emit electromagnetic radiation. And in fact, that radiation, as it moves, can use another fancy word, can be polarized. So if an electromagnetic wave is moving towards you like this, you see this going up and down like this, or you can see this going side to side like this. If I take two waves and I have one going like this and I have one going like this, and their timing is off by 90 degrees in the timing, and you look at it, it can look like a circle, and that's called circular polarization. I can do it in another way, and it can go in the other direction. So we have glasses called Polaroid glasses that can actually select one over the other by absorbing polarization of one direction, polarization of the other. So imagine your Polaroid glasses is space and space itself. That space can act like a Polaroid glass, Polaroid glasses.
Just let me get this straight. Space acts like Polaroid glasses.
That's right.
Good, okay.
A three-dimensional one, though. An expanding Polaroid glasses.
I got it.
Yeah. I don't know who's wearing the glasses, but that's a different story. But so in the early universe, it's expanding. And space, the fabric of space itself, is acting like a Polaroid.
Okay.
Like Polaroid glasses. Now, the gravitational radiation is very similar to electromagnetic radiation. It can have a polarization in this direction and in this direction, too. We call it circular polarization. But what happens, let me also say another thing. The gravitational radiation interacts with matter and antimatter in a way that polarization in this direction interacts with matter, and polarization in this way prefers to interact with antimatter. But the space is a Polaroid glasses. It's only going to select gravitational waves of one polarization. And now I want us to now take this picture. For those of you who love surfing, I mean, I can't surf. I tried, almost died. But you know, I like watching surfers. And there's another idea now. Think of the ocean waves at the beachfront, a long beachfront. And now you have surfers and anti-surfers. And the gravitational waves that get to shore is the universe today. So the surfers that are riding the waves and the anti-surfers fall down because gravitational waves of one polarization get to shore. And so the surfers that ride the gravitational wave that get to shore is the matter that's created that we see today. And so so this analogy actually applies directly to the equations that my colleague Michael Peskin and Mohammed Sheikh Jabari and I calculated using Einstein's theory, and it turned out that we got the correct number, the correct amount of matter produced in the universe. It was magical.
Stefan, let me go back to make sure I've got a good idea of this. The way you're suggesting is that in some way the universe works like a filter, like a Polaroid filter, which only allows certain sorts of gravitational waves to come in.
The space-time fabric itself.
Space-time fabric.
Yes.
And in some ways, this is like surfers who are on cool waves. They can get on the wave and cruise right into the bay. But the poor antimatter surfers, they just don't make it because their waves are in a big mess and they collapse and wipe out, basically.
They got wiped out, yeah. So I guess we're the cool surfers.
Right. And so, in fact, this whole idea of... Wait, yeah, you're the cool surfer. This whole idea of the amount of matter may be directly linked to gravitational waves and their interaction with the space-time fabric.
That's right, and it's not enough. Wow. It's not enough to just have the theory. We need to test the theory now.
Yeah.
And we have future experiments. We have my colleagues at the Center for Gravitational Wave Physics at Penn State and colleagues at SLAC amongst a worldwide search.
Wow, looking forward to that. But I think you have another way of demonstrating this.
That's right.
You've got your horn here.
That's right. So we all know that music boils down to waves. So I'm going to play what I call a gravitational wave blues.
Whoa.
Oh, look at that. I'm going real quick.
So, Stefan, I could really feel those gravitational waves. So, thank you very much indeed for your explanation. It's been wonderful having you here. And I'd now like to call up my next guest here from the Exploratorium here in San Francisco. And it's Keelan O'Connell. Hi, Keelan. So, the first thing we have to do with Keelan is everybody out there all over the world should know that Keelan has just been awarded her doctorate from Stanford University, and we give her all a big round of applause. Thousands of people around the world. So, Keelan, what you do is slightly different, certainly different from what Stefan does, and a little bit different from what we've been talking about, is that you are what we call a machine physicist, which actually means an accelerator physicist.
Yes.
So, what are accelerators for? What do we use these things for?
So accelerators are basically like your computer, your microscope, your pen and paper. It's a tool. It's a tool that we use to better understand the universe. A little bit more complicated and a little bit more larger than your standard microscope and computer, but basically doing the same job, which is trying to better understand matter, antimatter, where everything comes from.
And what about the accelerators we've got at the moment? These things which are working well, are you happy with these accelerators?
They're working well and they're doing great science and continue to do great science, but being that we're physicists and constantly pushing the edge of the envelope, the question is can they do better? Can we make them do better? And can we design accelerators that do the job better?
And in fact, that's what you do, isn't it?
That's what I got my PhD on.
Oh, great.
Building the better mousetrap.
And a kind of day-to-day job when you were working down at SLAC there in our Final Focus test beam, what were you actually doing in there?
I got paid to play with toys. Is really what I get. That's my job. You pay with these huge magnets and beamlines, and you try and build them better, and you try to take great data, and you try to push that edge of the envelope.
Right. And is this envelope being pushed? Because the thing about accelerators that strikes, I think, most people from outside our field, is these things are seriously big. Yes. That the LHC, the accelerator that's going to switch on in CERN in 2007, it's 18 miles in circumference. It's a massive piece of equipment. And Are they just going to get bigger and bigger and bigger and bigger and bigger?
That's one option, but my research that I did was actually to try and work on how to take a pre-existing machine and hopefully add a little upgrade to it. So you still use the same beamline, but you sort of switch things up entirely. You get more energy without necessarily needing the longer beamlines. But this is also very fringe physics. This is not going to cure the problem next year. It's definitely more of a long-term solution that we're working on.
Yeah. We've been talking a lot today, people around the world will have noticed, about surfing, which I guess is pretty Californian, that Stefan's been talking about it. How does an accelerator work?
Actually, the surfer is really the best sort of, off-the-cuff, easy way to explain it, which is...
Surfing explains everything.
It's a great sport in many ways. So basically, instead of having the ocean wave, you have something called an electromagnetic wave, which is basically replace the ocean, put in an electromagnetic wave, and just like the surfer needs to be on just the right part of the wave to ride it all the way to shore, you'd have the electrons or the antimatter positrons. You have to ride the just right point of the wave, and basically it can surf to shore. And sort of, as Niels was saying, these are really big machines, and sort of what we have are something called claistrons, which instead of just having one ocean wave, we have a little ocean maker. So every sort of 20 feet, it gets a little kick in the pants. The wave gets big and carries it all the way to the detector to actually take real data with.
And is this the way we're going to continue? But wasn't your research looking into new ways of doing this?
So for my research, instead of using the electromagnetic wave, which is working and works very well, and everyone, a lot of accelerators are based on this type of design, as instead of an electromagnetic wave, we'd actually have plasma. So that really great thing that gives you super fabulous televisions also might give you the accelerator of the future, where instead of, fabulous television, you actually get higher and higher energies and really sort of upgrade existing facilities by changing out the electromagnetic and putting in plasma. So that was sort of my very esoteric fringe field, which I'm sure you'll get an earful from the traditionalists.
Maybe so, but does it work? Did you get any results out of this new accelerated technique?
Great results, actually. We just published a paper recently that shows basically 1,000 times better accelerating gradients than what we use traditionally. Granted, this is not something that's going to be out on, available next year, but this is the first step and a proof of principle that this is really a viable option.
What does it mean, accelerating gradient? You say 1,000 times better gradient.
Yes. So that basically means you can get so much energy per meter. So that's a gradient. And so with our sort of traditional facility at SLAC, we get about 20 MeV per meter is the gradient. Mega electron volts are very strange unit of energy.
So we need a 2-mile-long machine to accelerate to a certain energy.
To a certain energy.
Right.
So you can imagine now you can either shrink that, or you can get 1,000, or you can double the energy basically with a minimal amount of distance right at the end, sort of as a little kick in the pants at the end.
And so your research has shown that in fact we can potentially make accelerators which would be 1,000 times more efficient.
Yes.
Do you have a patent?
Potentially.
Do you put a patent on this?
I wish. I believe I sold my soul when I signed up for grad school.
It's tough. That's great. Keelan, another interesting thing that you've been doing, is you've been writing a blog about your life. This is called Quantum Diaries. And indeed, Stefan is also a quantum diarist, which has been a very popular blog out there. And, indeed, sometimes 1,000 people a day come and read what you're doing. And, what interests me is, what is it like being a physicist? Here you are just starting off as a young person into a career of physics. What's it like? Is it a good job? Do you like it?
I love it. And I think the problem is a lot of kids, when they're, in 5th grade or 6th grade, they look at physics and think, no, that's not the way I want to go. I'm way cooler than that. And we're trying a little bit with Quantum Diaries and these types of blogging is to show that, we actually have lives. We're normal people too. We can hold conversations occasionally and sort of dispel that idea that, and really we get to play with these amazing machines, and we really see part of the world, that most people would kill to see some of the cool stuff that I've seen. So I think a lot of people don't realize all of the great options that you have when you go into physics.
Right. Maybe we shouldn't encourage them to kill.
Yeah, that's right.
I read one of your blogs, Keelan, recently, which was really very interesting. It was about a film that's just come out here in the States about kind of, the way that physics was seen. I don't know if you want to talk about that a little bit. But...
I'm a little embarrassed I rented this film. It's Ice Princess. Yes, it was intended for 13-year-olds, but it's a movie that sort of, I think, fits into the stereotype of, you're awkward and socially incapable as a physicist, but the moment you start, professionally ice skating, you get a little bit more attractive and more social, and it was just a commentary on how we need to change these types of movies for young boys and girls to see that, the stereotype isn't necessarily the actuality.
Did you buy some skates?
No. It would be a dire future for me if I head that way.
Great. Neil, we do have a couple of internet questions here.
Great. So, Keelan, thanks a lot. Let's go now
we should stay here because she can answer this question, which is what would happen to a person caught in the beam of a particle accelerator?
Oh. Not good things. Actually, we go to great lengths to ensure that no one is ever caught in the beam. In fact, we have a protection system involved that protects the machine itself and then also protects the people. So we don't even allow it the option to happen.
The second question we have is, if there were no energy, money, or space problems, how big would CERN, or I suppose SLAC, how big would you like your accelerator to be?
I actually am the person who I don't know if I'm the right person to answer this, just because my background is in advanced accelerator physics. So I'd actually like to see what's the smallest we can make our accelerator and still get incredible energies. I think that's the fun problem, and I think, although cool would just make it huge, but I think the more interesting problem is how small can we make it and still get these incredible energies and incredible science out of it.
I think there is another concept here that I think Keelan's quite right. It should be as small as possible. But there is a thing called synchrotron radiation, that when we make these particles go around corners in circular accelerators, then they lose energy. It's like a truck doesn't want to go around a corner. It likes going in a straight line. And you get to a stage where you lose so much energy coming off on synchrotron radiation that you've got to try and make your curves very gentle. And to make your curves very gentle automatically demands an enormous circle. And I think we probably more or less got to the end point that do people want to have machines that are hundreds of miles of tunnel? Probably not.
But we won't say if you give us the money to build it.
We won't say no. But I think the answer to that question really is not to necessarily go bigger, but really look into how to get smaller. Good. So when Paul finished and when Stefan finished, I didn't actually give any time for questions. And we have a bit of time now to see if there are any questions from our audience who is sitting out here at the Exploratorium, and indeed anybody else who's out there in the ether. I think we have a question here.
I have one question. If I understood Stefan's presentation correctly, could it be then, instead of the antimatter actually missing in the universe, it's just our inability to detect it because of this lens effect, this Polaroid lens effect that was explained?
That's a very good insight. Actually, there are types of matter, they're called neutrinos, and they don't have charge. And so in that sense, according to this model, there should be a lot of neutrinos out there in the form of quote-unquote antimatter. But the matter that we see today, it's a one-way, it's a unidirectional thing. It's very, we can talk about that after the talk, but that's a very good insight.
Good insight. The answer may be a little bit too complex for us at the moment. Any more questions out there? There's one here.
Paul, do you have a question? Go ahead.
So I think that the Stanford Linear Accelerator presents us with some really interesting aspects of Einstein's relativity theory. And I wondered, just what fraction, do you know what fraction of the speed of light the electrons are going at the end of SLAC?
I actually took the time to calculate this, and it was 99.9999998% the speed of light, I believe. There's 1 or 2 nines I might be missing, but it's pretty close to the speed of light.
So we're actually taking particles and getting them to speed. They're so close to the speed of light that relativistic effects become tremendous. I mean, the mass of those electrons, in our frame of reference as they're moving, that mass must go up tremendously.
Yes. Well, I mean, you can kind of think of it that we're making little big bangs, effectively. Nothing to worry those at home, but we're effectively making little big bangs and seeing what particles existed in that fraction of a second after the Big Bang, which is pretty remarkable. And the only way we're able to do that is to get to those energies and speeds.
So it's in essence, that kinetic energy, the extra mass of the electron when it collides, creates these particles.
A huge amount of energy.
And you're actually, it's really amazing to me, you were saying that this is a B factory. Now, when were B particles first made? Do we know when and where they were first? Were they made first at SLAC or?
No. I don't know the answer to that.
Do you know, I don't know where Bs were first made, but it certainly wasn't at SLAC. No. It may have been at Fermilab, or indeed it may have been in cosmic ray experiments.
But now you've got the factory here in Palo Alto.
Now we're cranking them out.
You're cranking them out, okay.
We really crank them out. I'll just give you one more gee-whiz figure about this, the speed of light. The LINAC is, the linear accelerator, is 2 miles long. Right. It then goes another mile around before it hits the accelerator. So this is 3 miles. And they're going at 99.999999
at the end.
Speed of light. If you shoot a rifle at the same time as you let these electrons go, then by the time the electrons have gone down the 3 miles, the bullet has gone about 3 inches up the barrel of the rifle. So these things are going really, 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 really fast. And what is one of the most amazing things about this kind of field is it goes beyond our normal sensitivities of touch, feel, sight, hearing, taste, smell. I think that's about it. You can't do any of those things in particle physics. Now, do we have time for one more question, or is it time to go back to our colleagues at CERN?
I have a question. I'm holding a mic. I actually have 2 questions. My first question is for Keelan. And I want to know, in her biggest dreams, what kind of machine she would like to build and to do what. And then I was wondering about Stefan. I was really intrigued by the music he played, and I wondered if there's some way that he can make play for me what matter might sound like and what antimatter might sound like, if there's like a difference between the two or not. The CP violation thing you talked about earlier, maybe just curious. So anyway, I wondered about those 2 questions.
To be honest, if I get to continue to be paid to play with toys every day, I think I've got a pretty good job ahead of me. So I'm not going to be too picky on which accelerator particularly that I get to work on, but I think the job in general, I'm pretty fortunate.
I would love to play something about matter. Let me say something very quickly. Probably the greatest sax player, John Coltrane, later on in his career, came up with the concept, or something called sheets of sound, which to me I think captures the essence of what matter is, which is matter is both a wave and a particle at the same time. So I'm going to play some of Coltrane's sheets of sound, which is combining basically the wave-like nature of sound and the packets of sound. So that's what I'm going to do right now.
Yeah.
Antimatter is reverse it up.
So, thank you all very much indeed. Thanks, Keelan. Thanks, Stefan. Thanks, Paul, for your wonderful explanations. Thanks to the Exploratorium. Thanks to the Stanford Linear Accelerator, which is thanks to the Department of Energy, who finances us, and thanks specifically to Stanford University. And now I think the time has come for us to go back to our colleagues at CERN